Hello, this is Jojo, and today I'll be presenting on variational autoencoders. Before we get into anything technical, I want to give a bit of intuition for what these models are actually doing and why they're interesting. From there, we'll get into the math that makes it all work and end with defining our key objective that lets us train the model. So before talking about variational autoencoders, let's first discuss the intuition behind the more basic deterministic autoencoder. The core idea is simple. You take input, compress it down into a smaller representation called the latent space via a neural network we designate as the encoder, then try to reconstruct the original input from that compressed form via a neural network we designate as the decoder. For instance, if we had an image of a 3 from the MNIST dataset, we might pass it through the encoder, which compresses it down into a compact latent representation. The decoder then takes that representation and tries to reconstruct the original image as closely as possible. In deterministic autoencoders like this one, given the same input, the encoder always produces the same latent point, and thus the decoder always produces the same output. This works well for reconstruction, but with real data, the latent space can become messy and discontinuous, meaning you can't reliably sample from it to generate new data. That's exactly the problem variational autoencoders were designed to solve. What if instead of mapping inputs to fixed points within our latent space, we map them to distributions? That way, the latent space becomes structured and continuous. For instance, imagine instead of mapping 3 and 6 to single fixed points, if our encoder maps each one to a Gaussian distribution in the latent space. Instead of outputting a single point, our encoder outputs a vector of means and a vector of variances. We then sample from the Gaussian distribution created with those parameters to get a latent point which gets passed to the decoder. This has applications specifically for the generation of new images. Because our latent space is continuous, we can sample from any part of it without issue. Furthermore, we can perform some conditional image generation. If we know what region of our latent space corresponds to a certain attribute, we can sample specifically from that region to generate images with that given property. Now that we have the intuition down, let's take a look at what's actually happening under the hood mathematically. So first, let's define our terms. X is our observed data vector in n-dimensional space. Z is our latent variable vector in d-dimensional latent space, where d is much smaller than n, capturing the compressed representation. And p of x is the marginal likelihood of the data with respect to z. The goal of any generative model is to form a good model of this data generating distribution p of x. And by the definition of this marginal probability, we get this integral. Unfortunately, the integral is intractable, meaning it's solvable in theory, but in practice it is not worth solving. Additionally, using Bayes' theorem, we could rewrite p of x as this term. The problem is, we don't know the posterior ground truth p of z given x, and we will never know it, so this form is also unsolvable. But we can try to approximate this true posterior, which we say is parameterized by theta, with an approximate posterior, aka our encoder, which is parameterized by its own parameter, phi, which our model will try to optimize. So let's get into a derivation. If we start by setting the log likelihood of our data equal to itself, we can then multiply both sides by 1, which is equivalent to multiplying the right side by the integral of q, because the integral of any PDF is 1. We can then bring the log into our integral because it doesn't depend on z. And now if we look, this integral is actually the definition of expectation of log p theta x over our approximate PDF. We can apply Bayes' theorem once again to the value inside of our expectation like we saw on the previous slide. And then picking up from the last slide, we can multiply both the numerator and denominator by the same quantity. And then because this can be rewritten as the expectation of the sum of two logs, we can separate them into two separate expectations. We can then substitute in the definition of Kullback-Leibler divergence. A quick aside to define Kullback-Leibler divergence. It is a measure of how different two probability distributions are from one another, and it has a couple of important properties, mainly that it is always greater than or equal to 0. After all that, we have this expression for the log likelihood of our posterior. We define the expectation term to be the evidence lower bound, or the elbow. Because we know that the KL divergence term will always be greater than 0, we know that our log likelihood will always be greater than or equal to the elbow, hence why it is called the lower bound. Thus, maximizing log likelihood is equivalent to maximizing the elbow, which will be our goal going forward. Rearranging the elbow further with Bayes' theorem, we arrive at this term, which we can then arrange our expectation once again to get this form. And we can split the expectation similarly to how we did it last time. And finally, we can substitute in the inverse of KL divergence, which is why that term is negative. We see now then that the maximizing the elbow will inherently maximize the first term and minimize the second term. Now we will take a step back and think about what each of these terms actually represents. The first term is our decoder. Given the latent representation z, it measures how well the decoder recovers the original input. The second term measures how far our encoder is from the prior latent distribution, pz. The issue is, when trying to maximize this term, gradient descent performs poorly due to high variance as shown by Kingma and Welling. Furthermore, we couldn't even run backpropagation if we wanted to, because we cannot run backpropagation through a stochastic or random sampling operation, such as the one included in the expectation of our second term. However, we can solve this issue with a new estimator via the reparametrization trick. So the main idea behind this trick is that we relocate the stochasticity out of our model parameters. Instead of sampling z from our approximate posterior, we define z concretely as the following, where epsilon is randomly sampled from a standard normal distribution. This allows us to relocate the stochasticity from the distribution whose parameters our model is trying to optimize to one with no learnable parameters, epsilon, allowing backpropagation to pass through cleanly. Then we can rewrite our definition of the elbow as the following, because sampling z from our approximate posterior q is now equivalent to sampling epsilon from a standard normal and plugging it in. It can be shown that this reparametrized parameter is an unbiased estimator of the elbow. And for completion's sake, this is the completely tractable form of our loss, which is equal to the elbow term that we derived.